Okay, now let's continue our part B. Yeah, part B. Okay, so now on questions 3, determine the forces acting on the beam at point P and Q. So we want to find the force on P and Q. So what are the forces on P and Q? Okay, refer to our free body diagram that we have just drawn. Forces on P, okay, just want to highlight on P and Q. Yeah, forces on P is the normal force because it's a smooth wall. Yeah, it's a smooth wall, so it only has the normal force. So forces on P is only the normal force. But forces on Q is a ground, okay, a rough ground. So it has the friction and also it has normal force. So combine this friction and normal force, we have reaction force Q. So for force on Q is actually the reaction force Q. We need to find the reaction force Q for point Q. Reaction force Q is actually the resultant force of normal force and also the friction. Okay, but P is only the normal force because no friction. Okay, so what we need to find is this normal force and this RQ. This is our target for question 3, normal force at P and reaction force on Q. Okay, to do that, we need to we need to apply the Newton's first law. Okay, for equilibrium of rigid body, which has 2 conditions to fulfill. Equilibrium of rigid body means the total force must be 0, okay, and the total torque must be 0. Remember, rigid body has 2 conditions: total force equal to 0, total torque equal to 0. So we need to draw a diagram, a table like this. So we need the table so that our working is more systematic. Always put all your table, all the information here, so your working are more systematic. So we have column Fx, Fy. Okay, this is all the force on X component, and these are the force on Y component, and these are the torque. This is the torque. The torque generated by all these forces. Okay, and then the below here is the resultant force and resultant torque. We know that equilibrium of rigid body, the total force must be 0. That means the total F in X component must be 0. The total F in Y component must be 0. And then finally, the total torque must be 0. So fulfill all these means equilibrium of rigid body is achieved. Equilibrium of rigid body, yeah? All equal to 0 means the rigid body is equilibrium. Now, okay, let us first look at Fx. Okay, look at Fx. So what are the forces? Look at here. What are the forces exist in the X component? Look at here. So in X component, that means the horizontal component. Yeah, the horizontal component, we have the normal force. Okay, hold on a second. Look back to our concept. Yeah, talking about all this. Total force equal to 0, Fx equal to 0, Fy equal to 0. How to know about the positive and negative sign? Look back to our concept. Newton's first law. Okay, talking about equilibrium of particle or point mass. Okay, equilibrium of rigid body. Okay, so for total force equal to 0, we have X component and Y component. Okay, just take the forces to the right as positive, to the left as negative. Going upward is positive, going downward is negative. Okay, so the horizontal is the X component, the vertical is the Y component. Okay, so very simple. Okay, go back to this one. So looking at here, we have what forces? For let's say let's say begin with RQ. Okay, RQ. RQ, it has 2 components. It has Rx and Ry. Okay, Rx is actually the friction. Ry is the normal force. Okay, so RQ, it has Rx. Rx is to the right. To the right is positive, isn't it? Okay, I just want to write it down here. Yeah, to make it simple for you. Okay, I want to okay, hold on a second. This one, I just want to put it here. Yeah, for reference. Okay. And about the talk, I also want to put it over here for your reference. Okay. So remember, these two refer to this one, and talk refer to this one. Okay. So now, so we know that okay, for RQ it has Rx. We only look at X component. RQ has Rx. Rx is to the right. To the right is positive. So we write as positive. We put as positive. Okay, positive. We put as Rx RxQ. Okay, RxQ. Now, how about the weight? The weight, does it have any? Okay, does it have any X component? No, it has no X component, isn't it? So we just put as 0. We just put as 0. How about the normal force P? Normal force P is to the left. To the left. So it has X component. So this is negative to the left is negative. Put as negative. Negative. Normal force P. Okay. This one we can drag a little bit down here. Right. So we have negative force P. Okay, this one is to the right and this one is to the left. You see, that's why it becomes 0. You must have one positive and one negative. Then only they cancel each other, become 0 to be equilibrium. You understand? You cannot have two forces to the right or two forces to the left. You cannot have two forces in the same direction. They must be in an opposite direction. Then they can cancel each other to become 0. So if the force on P is to the left, then the force on Q must be to the right. Then only to be equilibrium. You cannot say, oh, force on P is to the left, force on Q also to the left. Then surely this rod will fall down. Yeah, it's not equilibrium. Okay. Okay, good. One positive, one must be negative. Okay. So can cancel each other, become 0. How about Fy? How about force in the Y component? Okay. Look at RQ. RQ, it has forces upward. Forces upward. So that one is positive. Forces upward is positive. I put it as positive. Positive what? Positive RYQ. Okay, that's just that simple. How about the W? W is going downward. W is going downward, so it's negative. It's negative. Negative W. Okay, going downward. And then how about the P? Normal force on P. It has no Y component. So the Y component is 0. Is 0. Just put 0. You see, again, in the Y component, one is positive, another one must be negative. They must have opposite sign. You cannot have two forces going downward. The reaction force here must be going upward. Because the weight here is going downward. Must be opposite direction. One positive, one negative. Then only can cancel each other, become 0. This is the law of equilibrium. You understand? Equilibrium. One is they must have opposite direction. Then only they can cancel to get Fx0, Fy0. Understand? One positive, one must be negative. You cannot have both positive. You cannot have both negative. Okay? Good. Finish that. How about the torque? Torque. For torque, is special. Torque, we need an axis of rotation. Still remember the notes we learned before? Things can rotate because there has a fixed point. We call it a pivot point, we call it a hinge, or we call it an axis of rotations. Okay, something rotate, it must have a certain axis of rotation. So for torque, we need to determine a point for axis of rotation. Yeah, a point for axis of rotation. Actually, this point of axis of rotation can be anywhere. We can assume this rod rotate around point Q. We can also assume the rod rotate around point P, or we can assume the rod rotate around the center of mass. So this axis of rotation can be anywhere. Alright? But we need to take one point. We need to set one point for axis of rotation. Okay? So we to set the axis of rotation, we need to be clever. Okay, we need to be clever. We try to put the axis of rotation at the point which is the most complex, the point which has the most forces. You see, look at which point, the point P, the weight, or point Q. Which one is the most complex for us to put the axis of rotation? It's point Q. We put the axis of rotation there, okay, because there are many forces at point Q. So we put axis of rotation at point Q just because we have too many forces on point Q. Okay, you will know, you will understand. Okay, just want to tell you that this thing, I written here, axis of rotation can be anywhere. You can put at point Q, you can put at the weight here, you can put at point P. But we set axis at the point with most forces. So we see that point Q has the most forces because it has the friction, it has a normal force, it has two forces here. So we set the axis over here to simplify our calculation. That's the purpose, to simplify our calculation. Why we set at point Q? Actually, we can set at point P also. But why we set on point Q? Because we want to simplify our calculation. That's the purpose. We would just want to simplify our calculation. You will see why. Okay, we set the axis of rotation at point Q. Okay, and you must write down here. Yeah, you must write down here. Where do you set your axis of rotation? I write axis of rotation at point Q. I put my axis at point Q. Okay, now, okay, and you will see the magic happen. Yeah, why I set at Q is the best. Okay, okay, and before we want to we want to find the torque, we must also know about the torque first. Yeah, the concept of torque. Okay, of course, if you look at here the forces, normal force, the weight, and the reaction force, they are not perpendicular to the moment, perpendicular to the distance. Okay, so we need to resolve all these forces into the perpendicular components. Okay, so before we dive into resolving the forces, let us go back to our concept of torque. Yeah, how to make an object rotate. This is the one. Look at here. Back to our formula for torque, which is R cross F. Okay, F sine theta times R, which is FR sine theta. You know why is F sine theta? Because this theta is between the force and the distance. This distance we call it moment. We have a special name, we call it moment. Moment means the distance of the force to the axis of rotation. Okay, so now okay, why is it F sine theta? Why is it not F cos theta? Because look at this force. This force is resolved into two components. It has F sine theta and F cos theta. F cos theta is adjacent to the angle theta. F sine theta is opposite to the angle theta. Okay, so which force make the object rotate around this axis of rotation? Which force is responsible to make this object rotate? F cos theta pushing towards the axis of rotation, of course, cannot rotate the object. Only the F sine theta. F sine theta can make the object rotate. F sine theta is the perpendicular component which make it rotate. Always, remember, always the perpendicular component make the object rotate. So always the perpendicular component responsible for the torque. Understand? That's why when the theta is between, you see, when the theta is between the force and the R, when the theta is between force and the R, then we use F sine theta, because F sine theta is the perpendicular component to the R. Okay, this F sine theta is only when the theta is between, look at the theta is between the F and the R. Okay, we use f sine theta. However, there are certain situations that the theta is not between the f and the r. You look at here, this is the f and this is the r. This theta is not in between. I give you the theta over here. Then for this case, this torque is not f sine theta anymore. It's f cos theta. For this case, when the theta is not in between f and r, then we just look for the perpendicular component. It's still back to the concept perpendicular component which make it rotate. Okay, so for this formula, it become what? It become the perpendicular component f cos theta multiplied by the r. Okay, for this one, it become fr cos theta. Understand or not? So it's not always f sine theta. Sometimes it is f cos theta. Depend on where is the angle. If the angle is between f and r, then we use f sine theta. If the theta is not in between f and r, then we use f cos theta. Okay. Anyhow, you just look out for the perpendicular component. So the perpendicular component can be f sine theta, can be f cos theta. So depend on where is the angle, theta. Okay. So always remember this basic concept. Always the perpendicular component make the object rotate. So always the perpendicular component responsible for the torque. Okay. Okay, good. So now go back to our questions. Okay. And I will also explain why we put the axis at the point with most forces. Okay, to make the calculation simple. Okay. So first of all, look at RQ. RQ. So okay. So what is the torque by RQ? What is the torque by RQ? Okay. So what is the torque produced by RQ? So what is the formula again? What is the formula again for the torque? What is the formula again for the torque? Torque depend on F times R sine theta, isn't it? So Fr sine theta. Look at here. Torque, when you see for RQ, it is acted on the axis of rotation. You know why I put my axis of rotation over here? Because you have RXQ and RYQ and it's complicated here. So why don't I just put axis of rotation here so that RQ acting on the axis of rotation itself. So when RQ acting on the axis of rotation, this is what happened. The R becomes 0. You see? The torque for RQ, the distance becomes 0 because RQ acting on the axis of rotation. Excuse me. The RQ acting on the axis of rotation. So the distance becomes 0. When distance becomes 0, torque is 0. So RQ, I don't need to think anything because the distance is 0. Yeah. So the distance is 0. So that's why, because distance is 0, that's why the torque is equal to 0. The torque is equal to 0. I just put a 0 there. I don't need to think anything. I don't need to find out what is RXQ. I don't need to find out what is RYQ. I just put 0 because RQ is acting on the axis of rotation. So simplify my calculation already. You see that? Simplify my calculation already. So there, the torque by RQ is 0 because it has 0 distance. Okay? Okay, good. Now, how about the weight? Look at the weight. What is a torque? So again, back to our concept, always the perpendicular component make it rotate. It can be f sine theta, can be f cos theta. So depend on where is the angle theta. Understand? So find the perpendicular component. So what you have to do is you have to resolve this weight into two components. Okay, two components. So we have the distance is, this is the distance. Okay, if you look at here, this is the distance. Okay, actually I don't want to make the picture become complicated, but you know, this is the distance. Okay, if you can see, this is the distance R. Okay, distance r. So you have to resolve this weight into the parallel component and the perpendicular component, and find out what is the perpendicular component. Understand? Which make it rotate. Okay, so find out the perpendicular component. So which one is the perpendicular component? Okay, let's write down. Yeah. So okay, so this W, it has you have, okay, hold on a second. Okay, I readjust my diagram already. Now, so we have to find out the perpendicular component. Okay, resolve this weight into the parallel and perpendicular component. Yeah, so this is the one. So you have the parallel component and perpendicular component. Understand? So resolve it, but we need angles. We don't have angles right now. So do we have any angles? Okay, good. I think what should I do is okay, I removed the RQ already because very disturbing. Yeah, I want to draw something here, but it's disturbing. Yeah, my drawing. Okay, I remove my Q. I put it somewhere else. Okay, the W here, I just want to focus on W because I want to find the torque on W. Okay, find the torque on W. So how? Okay, I need angles. I don't have angles, isn't it? First of all, what you can see here, we have angle theta from the beam. Given us the theta, isn't it? Do we give us the theta? No, he got the theta minimum. That's the theta minimum. Okay, this is the theta minimum. Okay, so this W, okay, we need to find angles. Yeah. So first of all, you can see this is a right angle triangle. See that? This is a right angle triangle. Okay, 90 degree. So what is the angle theta over here? What is the angle theta over here? Okay, what is the angle? What is the angle over here? This is a right angle triangle, isn't it? So what is the angle over here? It must be, that angle must be 90 minus theta, isn't it? 90 degree. This is a triangle, right angle triangle, and this angle must be 90 minus the theta over here. So in other words, but however, this question doesn't give us the theta. Quite tricky. Yeah, this question doesn't give us the theta, so we cannot really, we don't want to write our angle 90 minus theta. Very troublesome. So what we do is we find another angle, okay, which is the other angle. Since we want to find the perpendicular component, okay, this is the perpendicular component to the beam. So can you see that this is like parallel and perpendicular, like x and y component, the parallel and the perpendicular. So this also 90 degree, right? This is also 90 degree, isn't it? This is also 90 degree. So we can use this angle instead. We use this angle. So what is the purple angle? What is the purple angle? The purple angle actually is also theta. It's also theta, which is the same as the theta over here. Do you agree with me or not? You see, this angle here is 90 minus theta. So this angle is 90 minus theta. And yeah, use your common sense. Yeah. So very hard to explain. So this parallel and perpendicular component, they are 90 degree. So when we want to find this angle, we use 90 minus the theta here, or just use the 90 minus theta over here. We get the same angle. 90 minus theta. So we can say this angle here, the beam, the angle theta by the beam, is the same angle as the angle over here, theta. Understand? So okay, solve. We got an angle theta for us to resolve our weight into parallel component and perpendicular component. Okay, so rub off the rest. Okay, hold on a second. Okay. So I have readjust a bit. So this, okay, remember this angle here is the same as this angle. Okay, I already explained just now. Yeah, this angle, this angle is the same angle with this angle theta. Okay, so this angle theta will help us to resolve our force. We need to resolve our weight into parallel and perpendicular component. Okay, so this weight it has a parallel component, and it also has the perpendicular component. Okay, so what is the parallel component? First of all, look at here. This angle theta. Now this is, you see, this is the distance r. This is the distance r. Okay, distance r. So this force, this angle now, you see the angle theta is not in between. It's not in between the weight and the distance r. It's not in between. So that's why I say for torque it's not always f sine theta. It's not always f sine theta. It can be f cos theta. Because if the angle theta is not in between the f and the r, it becomes f cos theta. Understand? We just have to find the no matter what, no matter it is f sine theta or f cos theta, we just have to find the perpendicular component to multiply. Understand? So for this case here, the theta now is not in between the force and the distance. So the theta is outside. The theta is outside. No matter what, just find the perpendicular component. So what's the perpendicular component of force to the distance or to axis of rotation? Let's write it down. Okay. Let's write it down. So the perpendicular component is actually W cosine theta, because it is adjacent to the angle, and then the parallel component is W sine theta. W sine theta is parallel to the component. However, this W sine theta is parallel to distance. It cannot produce any torque. This W sine theta cannot rotate the object. So the thing can rotate the object is only W cos theta. Only the W cos theta will rotate the object. Rotate which direction? Look at how it rotates. This is the axis of rotation. So this W cos theta actually rotated clockwise. It rotated. We can draw like this. Like that. It rotated clockwise. You see that? It rotated clockwise. So I draw from, you know how I draw this one? I draw from the axis of rotation, and then I follow the force. From the axis of rotation, follow the distance, and then follow the force. So this thing will rotate clockwise. Yeah. This W cos theta, axis of rotation. You see, this whole beam is fixed at this point. Assumed to be fixed at this point, and this W cos theta will make the object rotate clockwise. So, okay. Back to the, clockwise is positive sign or negative sign. Clockwise is positive or negative sign. Look at this one. Clockwise is negative sign. Anti-clockwise is a positive sign. Anti-clockwise or counterclockwise is positive. Clockwise is negative sign. Okay. So this is a negative torque. Because it's clockwise is a negative torque. Yeah. So we put as this is a negative torque. Okay, because it's a clockwise. Okay. So can you find the okay? So what's the torque by the W? So let us write it down here. Yeah, let us write it down here. Torque by the weight. The torque by the weight is negative because it is clockwise. Understand? Clockwise you put negative sign. So it's negative. What's the force? We don't use f sine theta. We use for this case, because the theta is not in between the force and the distance, so we use the perpendicular component, which is W cos theta. Okay, so the force is W cos theta. The W sine theta has no function at all. Yeah, it's the perpendicular component W cos theta, make it rotate clockwise direction. Okay, so write it down here. W cosine theta. W cosine theta multiplied by the Distance. How far is the distance? What's the R here? What's the distance here? Yeah, it's half of the length. Do you give you the length of the beam? Give you the length of the beam? Do you give you? No, he just give you the weight but no length, right? No length of the beam. So what can you do? You don't have the length. Don't have the length, never mind. We just put length divided by 2. The R here is just because this is the center of mass, isn't it? Center of mass. So it's the length, the total length divided by 2. So we just take L divided by 2. L divided by 2. So that's it. That's the answer. Okay, we got it. Okay, we just put length. Never mind, because later on we can cancel the length. Yeah. Let's see the equations later on. The common terms like length can be cancelled. No worry. Okay. So we solved already for this one. We solved already for the torque by the weight. Now we have the normal force here. We have the normal force here by the last one, torque. Just now the Q, the reaction Q is 0 torque. Okay, the weight has a torque, which is a negative torque because it's clockwise. It rotated clockwise. But how about the normal force P? So how it rotate? Of course, it rotated anti-clockwise. You see that? If one clockwise, another one must be anti-clockwise. Then only can be equilibrium. Total torque equal to 0. One clockwise, one anti-clockwise, one positive, one negative. They cancel each other, become 0 torque. You understand? That's how funny is it? Not funny lah. It's the common sense. Okay. Okay. So let us find out what is the. We need to resolve this force also. Normal force into parallel and perpendicular component. We need to resolve this force into the what? The parallel component and perpendicular component. We also need the angles. We need angles. So if you look at this angle, we can use this angle also. Theta here. This tan theta and is equal to this theta. Is equal to this theta. They are corresponding. No, they are alternate angle, isn't it? Alternate angle. Yeah, this angle theta is the same as this angle theta because they are on the same horizontal line, same parallel line, So this angle theta is the same as angle theta here. So again, we can resolve this into this normal force into two components, parallel. Okay, draw a line first. Parallel component and perpendicular component. So we have a parallel component and perpendicular component. So what is the parallel component? Parallel component. This time the force and the distance. Okay, the angle theta is between the normal force and the distance. You see that? This one later on you will find out this one is n sine theta. Using sine theta. This one is theta between the f and the distance. The perpendicular component becomes sine theta. Okay. Back to the original formula. Okay. Because this time the theta is between the force and the distance. So you see the perpendicular component. Because it is opposite to the angle theta, it becomes normal force sine theta. Because opposite to the angle, the parallel component becomes normal force cosine theta. But we know that the parallel component cannot rotate the object. It has nothing to do. So what important is only the perpendicular component, and sine theta will make the object rotate anti-clockwise. If you look at, imagine, just use a pen here, you fix a point here, and then you just push it in this direction. This beam will rotate anti-clockwise. So I just draw from the axis of rotation, and then I follow the force from the, okay, let me draw again. From the axis of rotation, follow the force. See that? From the axis of rotation, follow the distance, follow the force. So you see that this is anti-clockwise. Anti-clockwise is for anti-clockwise, it is a positive torque. It's a positive torque. So we label it as a positive torque. Understand not? This one will make the object rotate anti-clockwise. So it's a positive torque. Okay. So now, so what's the torque? Just put as it's a positive torque because anti-clockwise. Okay. You see, one positive, one must be negative torque. Then there be torque equal to 0. Okay. Okay. Write properly. Sorry. Okay. So what is the force? The normal force sine theta. Okay, just write it down. Normal force sine theta. Okay, and then multiply by what? Multiply by the, how far is the normal force from the axis of rotation? How far? How far is it? L. The total distance is the whole length, L. Just now from here to here is L over 2. From here to here is L, the total length. So that one is L. L. Okay? Remember that. So using the formula FR sin theta, okay, we got this. So this is our torque. This is our torque for point P. Okay? So we already got all the forces here. Okay? You see? This torque also has one positive, one negative, anti-clockwise and clockwise. You cannot have both. You cannot have both. You cannot have both turn clockwise or both turn anti-clockwise. Cannot. Yeah. One must be clockwise, another one must be anti-clockwise for the object to be equilibrium. Okay. You see, to be equilibrium, must have one of it must have positive, the other one must have negative. Then only can cancel each other. Become zero force and zero torque. Okay, that's all for this part, part B. Later, part C, I will solve the questions to find all the values. Thank you for your attention, okay, and your time given. Thank you.